So, an extremely interesting topics concerning the polarization is the linkage between the polarization, so actually the action to induce a certain polarization with a specific instrument on an electrode. Well, this polarization is directly connected with the Fermi energy. In which way? So, before I start speaking about which is the link between Fermi energy and polarization, it's important to remind a little bit what is the meaning of Fermi energy. And so, if we are considering, for instance, maybe a metal based on the free electrons model for the quantum descriptions of it, we can imagine that this metal is composed of different number of electrons. And if we want to be able to obtain the total number of electrons, we need to consider the density of state for each single energetics level and the probability of occupations of this state, integrating this result for the overall energy. So basically, the Fermi-Dirac distribution, this equation here, this function, is basically a statistic function that describes for each single energetic level which is the probability of occupations of each single energetic state. So basically, the Fermi energy is a value present in the Fermi-Dirac distribution function, this one, and is an extremely important reference value for the descriptions of material, and in this case for descriptions of the electrode. Why? Because the Fermi energy, it represents the energetics level at which we have 50% basically as probability of occupation concerning the energetic state, the different state present in a certain energetics level. So if we want to define this with a picture, so we can imagine that for each single energetics level we can have a certain number of state, and so the number of state for each single energetics level on the unit of area is defined as density of state, described in this case not an orbitalic state, because in each single state we have only one electrode, and the probability of occupation in each of this single state is described with this function. So we can have maybe one electrons here, one electrons here, one electrons here, and so on, and maybe for this energetics level this value is equal to 1. So we have that each single energetic state for this energetics level E1 is completely occupied. We have 100% of occupation. But maybe we can have even something like this. In this case, the probability of occupation for a higher energetic level is smaller, and maybe is 0.7, is 70%. And maybe sometimes we can even have a situation in which only half of the energetic state are occupied. Well, in this situation, we are looking for the Fermi energy. So the Fermi energy is the energy at which the probability of occupations for each single energetic state present at this energetic level is 0.5. So we have the 50% of occupations probability. And this is a reference value that is extremely important. Why? Because it's able to quantify basically how much we are enriching a system with electron during a polarization. But before do this, and it's important to say that this is also reference value, since is always the same value regardless the temperature. We can increase the temperature and we can decrease the temperature, but the Fermi level, the Fermi energy will be always the same. And in particular, when we are decreasing the temperature, reaching 0 Kelvin, in that situation is not only the state having probability of occupation equal to 50%, but is also the last occupied. How we can understand this concept? We then couple this picture with the analytical resolutions of this function. So we have, for instance, the analytical resolutions of this function, energy versus probability of occupation, and we can say that for a certain value of temperature, we can have this analytical trend. Something like this. And the Fermi energy is obviously the energy of the energetics level at which the probability is 0.5. What is important here is that if we increase the temperature, for instance, or if we change the temperature, we decrease the temperature, or we increase the temperature, so we are going in this direction by rising up the temperature, what is happening is that the Fermi energy is still remain always the same. And at the same time, when we are approaching 0 Kelvin, we have this profile. What does it mean? That the Fermi energy is again the energy of the level in which the probability is 0.5, but at the same time is also the last occupied energy level. And so basically we can have something like this if we are maybe these are the different type of energetics level, and each of these energetic level has their own probability of occupation. So we have A1, A2, A3, A4 and A5. And this blue point, it represents an electron. So we have, for instance, here a probability of occupation that is maximum. We have here a little bit higher. We have here something a little bit higher. And here we have the Fermi energy. This is the Fermi energy, because we have only half of energetic states that are occupied. But maybe we have even a higher energetic level that is occupied even with a smaller probability. Maybe if we are at a temperature that is different from 0 Kelvin. When we are approaching 0 Kelvin, this value is also the last one, in accordance with the profile of this function.